So now let's do a slightly different variation on the same problem. Exact same numbers, but we're going to change the way the question is stated just a little bit. So according to a recent government survey, the daily commuting distance of all U.S. workers across the nation averages 13 miles, with a standard deviation of 13 miles. Same population variables. The mean of the population and the standard deviation of the population are the same as in our original problem. But now you're a developer working in New York, and you want to know whether the daily commuting distance of workers in New York, in the New York area, is longer than the national average of 13 miles. So do the commuters in the New York area, do they commute a longer distance than the national average? Here that word longer should key you into what type of test we're going to be doing. We only care if the New York area workers are commuting a longer distance. You obtain the same sample, you get the same sample mean. 169 workers, the mean is 15.5 miles. Now you're going to test the null hypothesis at the 0.05 significance level. But here's where things are going to change. You have to set out a different research problem. And here it is. Does the commuting distance of all New York area workers exceed the national average of 13 miles? That's one way to state this. You could say, does the commuting distance of all New York area workers, is the commuting distance of all New York area workers longer than the national average of 13 miles or greater than the national average of 13 miles? You could state this in a few different ways, but what we're wanting to say is that we're only caring about it. What we want to know is if it's longer, if it's a larger commute, a longer commute. So given that we've done this and set up this research question, the research problem in this way, we're going to do a different type of test. We're not going to do a two-tailed test now. Instead, we're going to put out the statistical hypotheses for a one-tailed test. We only care about the high-end tail, whether it's a greater distance. So here, look back to your notes. So we'd set aside the null hypothesis as the population of New York area workers having a commute less than or equal to 13 miles, so that national average. The alternative hypothesis is that the population mean for New York area workers is going to be greater than 13 miles, greater than that national average. So we only reject the null hypothesis is if we have evidence that the New York area workers are commuting longer than 13 miles, not longer than the national average. So again, look back at your notes, make sure that you see how this sort of hypothesis, these statistical hypotheses were written, given that we're doing a one-tailed test and we care about the upper tail. So now we set aside the decision rule. Again, this is going to be slightly changed, given that we're doing a one-tailed test. So here, we're going to reject the null hypothesis at the 0.05 level of significance. We're still testing at 0.05 level. If z is equal to or greater than 1.65. Now remember, for a one-tailed test with an alpha of 0.05, the critical z-value is either going to be plus 1.65 or minus 1.65. And because of this example, we're testing whether the distance is greater than the national average. We're testing that one-tailed upper test. We use a critical z-value of 1.65, the positive version of it. Okay, so now you can see that your statistical, both your research problem, your statistical hypotheses, and your decision rule have been slightly altered given that we're dealing with a one-tailed test. Same format, just slight alterations. But now we do the calculations. Calculations are performed exactly the same way for one-tailed and two-tailed tests. You're still using the same formula. You're still having all the same values as the last example. So here, all the calculations, they're good. It doesn't matter whether you're performing a one-tailed or two-tailed test, you're going to do the calculations the same way. So I won't go through this. We still get a z of 2.5, positive 2.5. So now we come to our decision. Here we can decide to reject the null hypothesis because, right, we can reject it at the 0.05 level of significance because z equals 2.5, and that's greater than 1.65, our critical z value that we needed from the decision rule. So we can reject the null hypothesis. And now we go back into plain English and interpret this. You can see this is going to be slightly different. The mean commuting distance of all New York area workers is longer than the national average of 13 miles. Here we can talk about the direction. Here we can say it's longer. In the two-tailed test, all we could say it was different than the national average of 13 miles. Here we can conclude that it is actually longer than the national average of 13 miles. Okay, so if you're still looking for extra examples, you can check out question 10.6 in your book for another example of using z-test and the hypothesis testing summary format. And just as a hint, this one is going to be an example where you're going to actually retain the null hypothesis. The answer is in the back of the book, so you can go ahead, solve the problem in the way that we've just done, the way we did in class, and then you can check your answers in the back of the book. So here, you're going to find an example of retaining the null hypothesis and what that looks like. Additionally, I'd like you to think about, if you want more practice, think about redoing this example problem with a different level of significance. So maybe with alpha equaling 0.01, the other main alpha level, significance level that you'll see in behavioral and medicine statistics. So when you do this, think about what parts of your hypothesis testing summary would change if you change the significance level. And would you come to the same decision? Would you still reject the null hypothesis under both of these conditions, a one-tailed and a two-tailed test? Remember, the calculations, the z-score, isn't dependent on alpha. Alpha, the level of significance, is going to affect all of the decision rules, and it's going to affect the decision rules. So think about it that way. If you have any questions after you've done this, or you want me to check your work, please come and visit my office hours or set up an appointment with me. It's also fine to do this work with a friend and see if you both come up to the same conclusion. And in this example, if you get here and you want to either scan in or write out your 6 steps when you've changed the alpha level and redone the original example here, this commuting example, feel free to email it to me and I can tell you whether it's right. If it gets off too far, I might end up asking you to come in and talk to me about it. But you can at least ask me, is this right? And I can tell you yes or no. If you get the answer of no, you might want to come in and have a meeting with me. Okay, well, good luck, and